Hello, I'm Michael O'Connell, and this is going to be my second video regarding vapor-liquid equilibrium. And at the beginning of this video, I would like to examine the equations that we found in the last video. And basically what I'd like to do is go into Python that I've prepped here in Colaboratory and start writing some code. Specifically, I want to define functions to compute the bubble pressure, bubble temperature, dew pressure, and dew temperature. So let's start with that. So remember, we had a mixture of benzene and toluene, and obviously, as you can see at the top of the screen here, I have everything imported that we're going to need. So I have our link from GitHub. We are using CHE tools, as usual, to get the data we need for benzene and toluene, and then we're using the properties class as well. So, and the other important thing I should call your attention to, especially for this video, is we also have the root solver, which we will definitely end up using here in just a second. But let's create an array, and we'll call that X. So these will be our mole fractions in the liquid phase. And then we will do one for Y as well, which we can have the same fractions here again. Okay. All right, so we have those. So let's start with the easiest one, which I think is going to be our bubble pressure. And as I said when we were deriving an expression for the bubble pressure, we have to ask ourselves what we know, right? And remember, that was the left-hand side, right? Because we have all liquid, we know X, we know our mole fractions in the liquid phase for each of our components. And of course, we know the temperature, right? Because we were doing that isothermal expansion to find the bubble pressure. So we can start with that for our function. And then what do we want to return? Well, this is going to be extremely easy because we already have our expression right here. Basically, we want to return this sum, and fortunately, with CHE tools and the properties class, that makes this even easier to write. So we can use numpy for the sum, but basically this is going to be X, or mole fraction for each component, multiplied by the pure saturation vapor pressure. So this is P.Pvap, and then we'll put in the temperature there to pass that through. Great. So now we have our function for the bubble pressure. In the last video, we used the bubble pressure equation to derive an expression for the bubble temperature. What I'm going to do here for our bubble temperature function is going to be similar, because I'm actually going to end up using the bubble pressure function that we have already written. So this time for the bubble temperature function, we know the mole fraction of each component in the liquid phase, but we've been given the pressure. Now, the next thing I want to call your attention to is the bubble temperature equation. Let's take this right-hand side, this giant sum, and move it to the left-hand side. So we'll subtract it from both sides, set the right-hand side equal to 0. Let's take a look at this. We have the pressure that we already know, obviously, the mole fraction of each component in the liquid phase here within our sum, our Antoine coefficients, of course. But the one thing that we don't know over here on the left-hand side is the bubble temperature that we're actually trying to find. What if we can use something within Python that can figure out what this bubble temperature needs to be such that this equation is equal to 0? And of course, we know that what we can use for that is going to be the root solver. So what we can do is nest another function within our bubble temperature function such that we have an equation in there that we can use the root solver on to find what bubble temperature makes that equation that we'll write equal to 0. So let's see what that would be. Let's define our function for an equation. We will use a vector because we have to use a vector for the unknown for the root solver because it's used to using multiple unknowns. Now this time we're just going to specify that this vector is just the unknown temperature, okay, because we only have one unknown this time. Now what are we going to return? As I said, this will be the equation that we want to drive to 0. So what will this be? Well, this is going to look exactly like the expression I have here for the bubble temperature that we found in the last video. Now, this expression here, there's no reason to be afraid. This is the same as this, right? This expression, this part here, is the pure saturation vapor pressure, which we can find using P.Vap and then putting in the temperature. Now, of course, this time the temperature is unknown, but as we see, this is multiplied by the mole fraction of each component in the liquid phase. So basically, this is where we're going to use the bubble pressure function. So let's put that right in our code here in the return. We'll pass through that unknown temperature, right? And that's the value that the root solver is going to be adjusting until it finds the right temperature that sets this equation equal to 0. So what are we subtracting? Well, we're going to subtract the pressure that we're specifying, right? The pressure that we know, that's this P right there. Okay, cool. So that should work very well for us. Now, what do we need to return to just finish off this function once and for all? Well, this is where we want to use the root solver, of course, right? Because we want to spit out what the bubble temperature is for this pressure given the mole fraction of each of our components in the liquid phase. So we have the root solver. We need to put in the equation. That's EQ. Then the last thing we need to do is specify a guess for our unknown temperature. And I'm just going to use room temperature 298 kelvins. We'll take the X attribute out of this and obviously use the square brackets and the 0 to get that out of the vector form. And this function should work perfectly to give us the bubble temperature. So the next thing we are going to do is do the same thing, except we are going to define functions for the dew pressure and the dew temperature, and this will look very similar to what we have already done, right? So let's define a function. We'll call it dP for dew pressure, and this time we know the mole fractions of each component in the vapor phase, and we know the temperature. And then what are we going to return? Well, I'm not exactly sure. Unfortunately, I saved what we have from the last video so that we have the expressions that we can use once again. Well, this is the expression for the dew pressure. So it's 1 over, and we'll use numpy again for the sum here. And this is going to be Y, because it's going to be the mole fraction of each component in the vapor phase divided by the pure saturation vapor pressure of each component, which for us is the P.Pvap, right, where we use the Antoine equation and we pass through our known temperature. Perfect. So now we have the function for the dew pressure. Now, what about the dew temperature? Let's think about what that would be. Well, you probably can already guess that this is going to be very similar once again, right? Because we know the mole fraction of each component in the vapor phase, but this time we're given the pressure. Now, once again, we are going to use the dew pressure equation to derive an expression. In this case, it'll be a Python function for the dew temperature. So once again, we're going to use the root solver. So let's define our equation EQ again. And this time we will use the unknown vector W. And obviously, this is going to be the temperature. That's the only thing that we don't know here. And then we are going to return the difference once again. This will look similar to what we have above for the bubble temperature, except this time we're using dP because we're using the dew pressure function that we have above. So Y comma T, and the temperature, that's what we don't know. So that's what the root solver will be adjusting. And then we want this to be subtracted from the pressure that we specify because this is the expression that we want to drive to 0. Then what do we want to return? Well, this is going to be the root solver again, our equation EQ, and then we will use 298 kelvins once again for the guess of the dew temperature. Okay, excellent. So now we have 4 functions. We have a function for the bubble pressure, the bubble temperature, the dew pressure, and the dew temperature. Now that we have code for those 4 functions, we're ready to dive into the meat of this video. And basically, we're going to generate a plot of the binary vapor-liquid equilibrium phase diagram at a constant temperature of 393 kelvins, then create another plot at a constant pressure of 150,000 pascals. So what exactly is this going to look like? Basically, the more volatile component of our mixture, benzene, has some mole fraction at the beginning, and that's what we're going to be adjusting on the x-axis for each of these plots. Then, what I want to investigate here is how the dew pressure, or the bubble pressure, is going to change based on the mole fraction of benzene that we have in our mixture at the start. And we are going to do the exact same thing for the dew temperature and bubble temperature. Basically, we're going to see how they would change based on how much benzene we have in our mixture at the beginning. As usual, let's start with the bubble pressure plot. So on our x-axis, we're going to be changing the mole fraction in the liquid phase for our more volatile component. So we'll call that x1, okay? And we can do that with Linspace. So we can go from 0, which would be no benzene, to 1, which would be all benzene. In both cases, we wouldn't have a mixture there, but that will be our starting and end point, right? And then we will have 10 points. So let's do 11 on the end of that. And then from there, we can compute the mole fraction of the less volatile component, because this is a binary mixture. So X2, the mole fraction of toluene in the liquid phase, will be 1 minus X1, right? So if I had 20% benzene in this binary mixture, then the other 80% would be the toluene, okay? We know the temperature, and we're going to do 120 degrees Celsius. That's going to be 393.15 Kelvin, okay? And then we can also find, using that known temperature, we can find the pure saturation vapor pressure of each component. So that will be for benzene and for toluene. So we can store that right there in that variable. The next thing we need is the list of bubble pressures. So we'll call that list BP. And then what do we need to write for that? Well, let's reference what we had from the first video, right? We had this sum, which is the mole fraction of the component in the liquid phase multiplied by its pure component vapor pressure. And because we just have 2 components in our mixture, this is going to be pretty easy, right? We'll just have X1, the mole fraction of benzene in the liquid phase, multiplied by its pure saturation vapor pressure. And then we'll index that as 0 because it's the first one that I have up here. So see how benzene is first, and then we have the other compound, toluene, so that's why it's indexed with 0. And then we're going to do the same thing for toluene, okay? X2, and then index this as 1. So that would give us a list of bubble pressures. And then now we are ready to actually plot this. I'm going to start this off with fig equals make subplots. And I'm going to specify that we're going to have rows set to 1 and columns set to 2 because we're going to have 2 plots, hopefully by the end of this video, right? So then we just need to do fig add scatter and specify our x. Now what's that going to be? Well, that's going to be x1, right? So we're changing the mole fractions of the more volatile component, that's the benzene. And then our y is going to be the list of the bubble pressures that we have. Then we need to put this in row 1 and column 1. And let's see what this looks like. Not too bad. If we recall the equation for bubble pressure, this plot makes perfect sense. The pure saturation vapor pressure of each component is basically fixed because we are provided with a temperature. And basically, we are just adjusting the mole fraction of benzene in the liquid phase. So as we steadily increase that, and since there is a product within this sum, as we increase the mole fraction of benzene in the liquid phase, the pressure, in this case the bubble pressure, is going to steadily increase linearly. So this plot makes perfect sense. Now let's see what we can do for the due pressure. So what we want is obviously a list of due pressures, and this time I'm going to use an empty list. And you might be like, why is he doing that? And the reason is this: we have to remember that when we're trying to find the due pressure, what we know is the mole fraction of each component in the vapor phase, not the liquid phase. So remember, we're not on the left-hand side of Raoult's law anymore. So we can't just compute the due pressure values the way we computed the bubble pressure values. So unfortunately, it's just not going to be that easy this time, but it's not going to be that hard, because what we can do is we can start with an empty list of due pressures, and then we can use a for loop, and we can just append on the due pressures that we compute using the due pressure function that we already have. So that is exactly what I'm going to do. Now, our variable here is going to be the mole fraction of our more volatile component, of course, in the vapor phase, and I'm just going to call this y1. What is the range going to be? Well, the range is going to be x1 again, okay? It's the same thing. We're adjusting the mole fractions of our more volatile component. So there's no difference there. That's not anything we have to worry about. So make sure you have your colon. I'm really just telling myself that because I'm certainly going to forget it, I'm sure. And the next thing we need here is we need the mole fraction of the less volatile component in the vapor phase, just like we had up here with x2 equal to 1 minus x1. So we needed the same thing. So we have y2 equals 1 minus y1. Perfect. The temperature that we know is already up here, so we don't need to put that in our for loop again. Now, what do we need to do? So we need to compute the dew pressures, and we can use that using our dew pressure function. As I said, the problem is that we need to have the mole fraction of each component in the vapor phase, but this needs to be an array, just like it was before when we were computing these dew pressures, right? So as you can see right here, this would take an array, and here, let me hover over it. See? So you can see that it's an array. I just want to make sure that's clear. So we can call this array y and just make a numpy array ourselves and put in the mole fraction of our more volatile component in the vapor phase and then the less volatile component. So now we have that, and then we can put in the list dp dot append. And now we can use the dp function, the dew pressure function. We can pass through the mole fractions of each component in the vapor phase and the temperature that we already know above. So that is excellent. Now, let me do this to make sure that we actually have a list of dew pressures. And we do. That looks like it's going to be very, very easy to plot for us as well because of what we've already done with the bubble pressures. And we can put this on the same plot, okay? Because that way we have pressure on the y-axis each time. Just one curve is for the dew pressure, and then the other is for the bubble pressure, of course. And then we'll just change that to list dp for the y that time, or this time. And we have that. That looks fantastic, okay? So we have that nice red curve, and that is basically modeling the change in the dew pressure at a given temperature based on the mole fractions that we have in our mixture of the more volatile component. Now let's generate a plot that has a dew temperature curve and a bubble temperature curve. I'm going to follow the same steps that I used to create a list of dew pressures. So we can have a list of bubble temperatures that is empty and a list of dew temperatures that is also empty. And let's specify our pressure because that is certainly something we're going to need here. That's going to be 150,000 pascals. Okay. That is good. Now, what I'm going to do here is use a for loop again and then just start appending the bubble temperatures and the dew temperatures that we compute to their respective lists. And the variable I'm going to use is z1, and I'm going to use this for both of them because, again, these are just the mole fractions that we're adjusting. So that's not the reason that we are using these for loops, okay? The reason we're using these for loops is so that we can use our functions to compute the values we need and append them to the proper list. So we'll just call this z1, and then the range, of course, is going to be the same. Don't forget the colon. And we can compute z2 as 1 minus z1. And now we are pretty much ready to go. So let's start appending. So we'll start with the bubble temperatures, okay? And we use append. And what do we need here? Well, we are going to need the bt function, right? And then what we're going to need here is an array that contains the mole fractions of each of our components, right? So I am going to create another numpy array, and this can just have z1 and z2, right? Parentheses a little wild there, isn't it? Let's see. Make sure I didn't... Okay, this should be fine. And then pass through what we know. In this case, it's going to be the pressure, of course. And so that is ready to go. And then we can do something very similar for the dew temperature. It's basically going to be the same thing. Just change that to D, and then that is going to be exactly the same. And then we're just using the DT, which is the dew temperature function that's going to compute our dew temperatures and append it to our list. So all of that should work perfectly, and we should be ready to generate another plot. All right, so let's try to make these real quick. I'm going to copy and paste these down below, and then obviously we'll put these in column 2. And then x is going to be x1 for all of these, of course, because we're just changing the mole fractions of our more volatile component. Then we can change this to list bt, and then this will be list dt. Let's take a look at what these end up looking like. Beautiful. Okay. Now, another helpful thing for me to do before I start talking about these plots is to name them. So let's do name equals bt. I think it's just name. I don't think it's anything too crazy for these. And we can just copy and paste these in there. So this is going to be BP, this is DP, this is BT, and then this is going to be DT. Let's see that that doesn't give me any issues, and it doesn't. So that way we have our legend over there that is accurate. Okay, now we're ready to talk about these a little bit. We already discussed the trend shown by our bubble pressure curve, so let's talk about the dew pressure curve. And as you can see, as we increase the mole fraction of the more volatile component in our mixture, we see that the dew pressure is going to increase. And that does make sense, because we have to remember that the more volatile component has that lower boiling point. So we're starting off with a mixture of all vapor with our two components. And I'm going to push down on my piston really hard until I reach a certain pressure that will create that first liquid drop. So if it's enriched with the more volatile component that has a lower boiling point, I'm going to have to do more work to have that first liquid drop form than if there was less of that more volatile component. So that trend makes perfect sense. There is an important thing that I said, which is that the mixture is all vapor at first when we're dealing with the dew pressure or trying to determine what it is, right? And that is important because we have to remember this axis here is representing the change in the mole fraction of the more volatile component in general. I didn't specify what phase that it would be in because it's going to vary. Because when we are talking about the bubble pressure plot, obviously you're starting out with all liquids. So this would be X1, right? This would be the mole fraction of our more volatile component in the liquid phase. Conversely, if we're talking about the dew pressure, we would have Y1. It would be the mole fraction of the more volatile component in the vapor phase that we're discussing. So if I had more time, and I can do this on my own after the video, I would probably change these X1s to be W1, something else, something that's arbitrary. That way, someone reading this code wouldn't get confused and think that the x-axis for each of these curves should be the mole fraction of the more volatile component in the liquid phase, when in reality it's going to depend on what curve you're talking about. Next, I want to talk about the bubble temperature curve because this makes a lot of sense, right? If we increase the amount of the more volatile component that we have in our mixture, then the temperature at which we're going to have our first bubble form is going to be much, much less. So I think that just makes sense because that component is more volatile. So it is going to boil a lot easier. So if we have more of it in our mixture, then we are not going to need a super, super high temperature, right, to get it to boil. Now let's talk about the purple curve with dew temperature. When we're talking about dew temperature, we have to remember that our binary mixture is composed of purely vapor, and we're trying to decrease that temperature until we form our first liquid drop, of course at a constant pressure. And for these curves, we are at 150,000 pascals. So we need to think about the fact that our more volatile component has a lower boiling point. So if our mixture is enriched with the more volatile component, then we need to decrease our sample at a constant pressure to a much lower temperature in order to see that first liquid drop form. Likewise, if we had less of the more volatile component, then we could see that first liquid drop form even at a much higher temperature. So I think that's all I have for today's video, and I hope you enjoyed watching and got a lot out of it. And I think that these curves with bubble pressure, dew pressure, bubble temperature, and dew temperature are extremely important to understand for chemical engineers. So I hope that this was very helpful for you. Thank you so much for watching.